So exam 4 is on Tuesday. And the topics will be up through the Clausius inequality. So those are problems that I'll give today. I'll keep the numbers small so you have time to study and stuff. And we have a quiz today. Then we have a quiz. I guess it must be November 30th. We have a quiz. So here's what we have left, I guess. So exam is on Tuesday. Turn in binders on Tuesday. We have a quiz Thursday, 11:30, I believe. And then exam 5, the final, is Thursday, 12, that'll be 14, at 11 a.m. Yeah, we have the room for 3 hours, but I'm not going to make it any longer than the other tests. And it's in this room, 1326. So, and as long as this isn't the worst of your 5 exams, this will replace your lowest score in addition to counting as the final, you know? So if your scores were 94, 92, 6, 93, and 95, the 6 gets replaced by a 95, and it counts as the final. Yep. Yeah. Yep. That's how it will be. Nope. It'll be like the other ones. And if while I'm on this, if anybody's looking for study strategies where, you know, now towards the end of the semester, you're going back over a lot of old material, what I would recommend doing is go through all the old problems, but first just like look at it, you know, look at the question, understand the question, and ask yourself, do I know the steps to do this? And if you understand the steps, if you're just like bang, 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 like, yeah, you feel good about it, don't bother to work through that. I mean, unless, you know, maybe some of you have time to work through everything, but as sort of a time-saving thing, just keep going through the problems like that until you get to the ones where you're sort of hazy, like maybe you do this, maybe, you know, then those are the ones to spend some extra time on. Okay. Yes. 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 If anybody, I would like to put them up. If anybody would mind sending me an email about what specific tables. Really? Oh, you do? Oh, yeah. Could you send me that? Oh, yeah. Okay. Yeah. Well, I'll put it on the dark net or whatever it's called. That would be incredible. Yeah. Thank you. That would be great. Huh. Wow. Huh. Must be hard to make money off textbooks these days. You're right. Yeah, it's true. Well, also, if anybody, I mean, it's probably easier to just click on D2L on the one table you're looking for. So if anybody can remember which tables you were looking for that weren't there, I'd be happy to scan them and put them up there. I don't remember which ones they were. I remember that coming up though. Right. So, any other questions about the end of the semester? Yes. Yeah, for sure. Yes, for sure. Um, at least a quarter of the class will get A's. So normally I don't have to curve it, but this is my first time doing this class, and so there's a better chance than usual that it'll have to be curved a little bit. But I haven't really looked at the overall grades recently. Yeah. Yeah. Well, we'll see. So, yes, I will make every attempt to be reasonable about it, I mean, I just think of like the grades I give are supposed to be like a way to communicate to transfer institutions, like who understood this stuff at what level, and so I try to make it reasonable cutoffs. I don't see any point in being like I'm the only person who doesn't believe anyone deserves an A or whatever. Like it's a way to communicate to other people, and so I try to communicate in the way that's accepted or whatever. Any other questions about the end of the semester? Yes. No. That's a good question. Thank you. I think I'll get that back to you Tuesday. I know that doesn't help you study but I just I'm doing what I can. So that's a good idea. Yeah. Yes, I'll do that. Yep. All right. So there's one question on the homework that I wanted to do for sure, and then I'd be happy to talk about other questions you have. But a couple people asked me about number one, and it's sort of an open-ended question. Like, I mean, it's sort of asking for a proof, but it's like at what level of detail proof do you want? Okay, so let me talk about what some approaches are, what I was hoping you would do. Um, so number one from the assignment. Yes, yes, and that is, and if it occurred to you in that way, and that's your answer, that's really all I wanted from that problem. Let me go through a more mathematical way of doing it. That actually I got from Tim. That was the same way, right? Yeah, right. Yeah, so let's just think through it sort of uh, intuitively and then think through it a little more mathematically. Um, so the question says, like, uh, says you have a power cycle from the cold reservoir um, rejects heat to the hot reservoir and does work on the surroundings. Um, So what I wanted you to, I sort of wanted you to think about this in the minimum, you know, it's just sort of an intuitive idea. And the idea is just that, the Clausius statement of the second law says that it requires work to move heat from a low to a high temperature. And so show that this is impossible. So, okay, yeah. So if you think about it, it doesn't really make sense. It doesn't make sense because it violates the second law of thermodynamics. So one way to think about it is, one way to do it sort of more rigorously is to say, set up the system. A reversible power cycle. In this case, the assumption that you're making is if it's impossible with a reversible power cycle, you'd certainly think it would be impossible if you added friction or irreversibilities to the system. So we'll start with that, but that's going to give us the ability to make the substitution that says QC over QH is equal to TC over TH. And so our system looks like this. So here's TH, here's the system, here's TC, and we're talking about heat, QC, going from the cold reservoir to the system, and then heat, QH, going from the system to the high temperature reservoir, and then work being done on the surroundings. So what we're talking about is each of these three variables being positive. Okay, and so we're going to go through the calculation using the laws and show that one of these can't be positive. Okay, so the first law of thermodynamics, if this is a cycle, well, I'll write it out. We have this is equal to this minus this. And let's rename this W so that these don't have the same thing. Workout. This is a cycle, so there's no change in energy. Q is the heat that's added to the system, so that's positive QC. That's heat that's added to the system. QH, we're supposing, is removed from the system, so that's minus QH. And then minus workout. And so you can rearrange this. The work out is equal to QC minus QH. And now we'll use the fact that QC over QH is equal to TC over TH. So you can rewrite, I guess let's rewrite QC as QH times the ratio of TC over TH. But notice that this is less than 1. And so you have that the work out is equal to QH times TC over TH minus QH. We're assuming that all these things are positive. These temperatures are Kelvin temperatures, so those have to be positive. The way that we chose our sign convention, all these values are positive. So this is all has to be less than QH. And so the work out has to be less than 0, I guess less than or equal to. But, you know, if you find that kind of stuff interesting, that's the way to do it. But I just really want you to have this intuitive understanding of, you know, be able to sort of think about what we're talking about. We're expecting energy to go from cold to hot. You need to do blah, blah, blah. Mm-hmm.
This implies that QC is greater than QH if you have positive work.
Mm-hmm.
To basically set a minimum equality, and that shows that the decreases.
Huh. Okay, yeah.
How I did it after.
Cool. Yeah, that's interesting. Mm-hmm. Yep. Any questions about that? Any other questions on the homework you'd like to talk about? Okay.
We talked about on number 5. I don't really have the sheet printed out.
How do you not really have the sheet? Don't you either sort of have it or not?
I have.
Oh, okay. Wow, that's good. That's pushing.
My biggest thing was so there's the 20 of the air outside the coils, and
then let me write it down so I remember and we all remember, and then we'll. Okay, so number 5. A refrigerator operates steady state with a coefficient of performance of 4.5, a power input of 0.8 kilowatts. Energy is rejected to the room. So QC is rejected to the room at 20 degrees Celsius. And surface temperature of the coils is 28 degrees Celsius. And we want to find the rate of energy rejected through the coils That would be QH dot. And the lowest theoretical temperature inside the refrigerator. We're trying to find the rate at which energy is rejected. And in a refrigerator, energy is rejected to the hot reservoir. Yes.
So it's the hot reservoir.
Yes.
So when that Celsius.
Yes. 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 And we want the lowest theoretical temperature, PC. And what you're always using as your system in heat pumps and refrigerators and power cycles is you're using the gas that's carrying the energy around. So so like in a refrigerator, the thing you care about is where the beer is. That's the cold reservoir. Okay. The room is the hot reservoir, and your system is the refrigerant that's moving around. And heat pump is the same thing. So what was your question?
Oh, I was just wondering what the oil temperature. I was just kind of looking around in it. And
You know, that's not the first time that we've had problems from the book that seem to just throw stuff in that doesn't come into it. I mean, that would come into it if you were going to somehow calculate convection or conduction, but
okay.
Oh, that's true. That's right. I bet you're right about that. Like refer, yeah. That's what I was sort of thinking too, but I think I like that explanation better actually. Like they just make it once and then. Okay, well, let's go through this one. Okay, so the first law of thermodynamics says the change in the, and I guess we're doing this, so this work in would be a rate of work. So we'd be doing this as the EDT is equal to Q H dot minus, nope, I'm doing that. So it would be, so this would just be, let's start from the beginning. So it's Q dot minus W dot. And steady state, so this is 0. And coming into the system, into the refrigerant, is the heat that you're adding at the cold reservoir, so that's QC. And then you're giving away heat at the hot reservoir, so minus QH dot. And then you are gaining energy through the compressor, so you have something like that. So 0 is equal to QC dot minus QH dot plus W in dot. We know that, so 0 is equal to QC dot minus QH dot, and the work in is plus 0.8 kilowatts. And the last thing we know is the coefficient of performance is equal to 4.5. For a refrigerator, what you're trying to accomplish is you're trying to pull as much heat as possible out of the cold reservoir. So this is equal to QC, and you're trying to do that with as little work input as possible. That's QC dot over work in dot, and that's QC dot over, we know what work in dot is. That's 0.8 times 10 to the third. So what's 4.5 times 0.8? So 3,600 in watts, yeah. And now we can go back to, so now we have everything we need to use the first law. So 0 is equal to 3,600 minus QH dot plus 0.8 times 10 to the third. So that is QH dot is 4,400. Yes. Mm-hmm. Yeah. Right. We're already using the first law of thermodynamics, and that two equations we're talking about, the expression for beta that I used and the one you used, you get those from the first law of thermodynamics. So, yeah. And actually, we were talking about, there was one question, I don't remember which one it was. It was like, say whether this is reversible, irreversible, or impossible. And one of the things was impossible because the first law wasn't satisfied, even though, you know, it was all like mostly about checking like second law stuff. But in that case, okay, so we got this, and then now we're going to assume that we have a reversible cycle. So beta max equal to QC over work in, and from, and these are all dots still. And if we use the first law of thermodynamics, we can rewrite QC as QH minus work in. So QH minus work in. We don't want to do that because we still need to solve for QH. So let's rearrange for something else. So work in where was it? Well, we have QC and QH, but we're trying to re-express this in terms of temperatures so that we can calculate the temperature at the. Yeah, that's what I was working towards, just that other form. So, yeah, what's the other form? Okay. Yeah, so we got TC over. You have to remember to put these in absolute temperatures. So TH is 293 minus TC.
That's 4.5 then. But beta max equal to 4.5. You do that. Or...
That's what I did. That is what you did? Yeah. Lowest theoretical temperature. I guess that's the idea, yeah. So all for TC. What do you get for TC there? 0.85. So minus 35 degrees or something Celsius.
Thank you.
Yeah. Any other homework questions? Yes.
I guess here we can do max equal to Q dot over
Mhm.
and that's still equal to the temperature equation. So even on your notes, you just have it not as the rate of Q equal to those T's. Either or works.
Yeah, that's fine. You can think of it as just like you're canceling out a bunch of DTs. Mathematicians don't like if you think like that, but we can think about it that way. Just don't tell people you're thinking about it that way. You know what I mean? Yeah. Don't tell whatever. Don't tell Tom or anyone. But you could do it all really the way you would do it. So anytime you do cheesy stuff like that where you're canceling out DTs like they're real fractions, the way you would really do it technically is through the chain rule. You just have to go all through, do the chain rule, and then you'd end up being able to cancel something in the end. Yeah. So it's a heat pump. And the heat pump is used to keep the inside temperature 20 degrees Celsius. So for a heat pump, well, it works just like a refrigerator. It's just that what you care about is the heat that's added to the high temperature rather than taken out of the low temperature. So temperature TH is 293, 20 degrees Celsius. The heat pump receives energy from well water at 10 degrees Celsius. So T cold is 283. And it discharges energy by heat transfer to the building at this rate. So QC, QH has a rate of 120,000 kilojoules per hour. over 14 days. The heat pump. So the total work in is 1490 kilowatt hours over those, the 14 days. And we want to figure out first the amount of energy the heat pump receives from the well water. So we want the total QC over the 14 days. We want the coefficient of performance. And we want the coefficient of performance max. C is the easiest one because we already can just do that. We have both of the temperatures. Okay, so the first law says, well, let's draw a picture of what a heat pump does. It looks like a refrigerator. So you have your high temperature, you have your system, and you have your low temperature. The room. This one's the system, the refrigerant. And this one is the well water. And then there's work coming in. And we have heat QC coming from the well water into the refrigerant, and then heat QH rejected from the refrigerant into the room. The first law of thermodynamics then says over a cycle, you have 0 is equal to the heat added to the system, so that's QC minus QH, minus negative work in. So 0 is equal to QC minus QH plus work in. We know that work in is 1490 kilowatt hours. And we know that so QH QH dot is equal to 120,000 kilojoules per hour. So we want to So kilowatt hours, this is kilojoules per hour. So that's 120,000. Like a kilojoule is a kilowatt times second divided by hour. So if we integrate this, well, let's get this into kilowatt. So let's just get this into kilowatts. So kilowatts per hour times seconds. So we're going to divide this by 3,600. So what do you get for that? What? Okay. And now we can say QH is the integral over 14 days. Of 33.3 repeating dt. This time is in hours. And so 33.3 repeating times the quantity 336 minus 0. So what do you get for that? Okay. Kilowatts is joules per second. The easiest way, the most foolproof way to do it, I always trap myself into trying to think my way through it and save. Like, why not just convert everything to seconds from the start and do it that way? But if we think of just watts as a unit, don't think of that as having seconds in it at all. Then you can think of our units are these things watts and these time units hours, and then you can just do the integral over hours. But yeah, of course, the safest foolproof way is just get everything in seconds first, and then you never have to doubt the way you're thinking about it. So we're looking for QC. So now we just plug this back into our formula. Says 0 is equal to QC minus QH plus WN. So 0 is equal to QC minus 11,200 plus 1490. And so what do you get if you subtract those? 9710, and that's in kilowatt times hours. And now it's going to be easy to calculate the coefficient of performance because we have all three of those energies. So coefficient of performance for a heat pump is we want to reject as much heat as possible to the high temperature reservoir, and we want to do as little work in as possible. So that is 11,200 divided by 1490. What do you do for that? Okay. And then in the ideal case, so gamma max is equal to can someone just tell me that formula? TH minus TC. So we have 293 over 293 minus 283. And so what do you get? 29.3. Any questions about that?
So the SI units for Q is kilowatts or is watts?
Yes, watts.
We have to convert that into watts.
You don't have to convert any. I mean, you can give your answers in any units you want, but I think, you know what, I normally, like, I was doing this up here, like trying to save time or whatever, so I did it like this, which probably ends up wasting time more than it helps. But when I'm sitting in my office doing something like this, I just put everything in SI units, so I know exactly what the units are going to be. It's much easier, I feel like, in the long run. Okay. Because we were given it discharges energy by heat at a rate. I mean, it tells you that it's a rate. And then if you look at the units are energy per time. The work is given in kilowatts per hours, which is energy over time times time. The times cancel out, and so it's given in units of energy. Kilowatt hours is a unit of energy. Right. That's right. Yeah. Any other questions? Okay, let me go through. Whose is this? Thanks. Let me go through these two derivations of some equations that are going to be important to us. And I don't know if we'll have time to do example problems, but this stuff isn't on the exam, so we can get to this one as we get to it. But what we know so far is, so back to entropy. We know that for an internally reversible process, the entropy at state 2, that's a capital S, this is an extensive property, is equal to the entropy at state 1 plus the integral from state 1 to state 2 of delta Q over the temperature. Or equivalently, ds, infinitesimal increment of entropy, is equal to delta Q over T. Okay, so these are the These are what we're going to be working with. And we're going to come up with some equations that when you first look at them, it's very hard to believe that they're going to be that helpful, but we'll do some examples of how to use them. So we'll use this in the first law to derive the PDS equations. And one thing to notice about this is the derivation requires an internally reversible process. But the resulting equations are general. Okay, so we're going to start with the first law. And we can write that as du, so we're assuming there's no kinetic or potential energy changes. Du is equal to delta Q minus delta work. Into this, we'll use the fact that d work is equal to PdV. And so we get du is equal to delta Q minus PdV. And then we'll use the fact that ds is equal to, this is still a capital S, ds is equal to delta Q over T. So we can substitute in for dq, who dq. That's why they call it delta Q, so you don't get like distracted every time you try to. Yeah. Okay, so du is equal to TDS minus P dV, and then just reorganize it. They're called the TDS equation, so that get that alone on the left, and you get TDS is equal to du plus P dV. Okay, so that's the first one. I'll call this one equation star. And so let's think about what it gives us. So it lets us calculate entropy in terms of temperature, internal energy, and pressure as a function of volume. Okay, so that's where this would be useful. Because to use this, you integrate it. Okay, so and we're used to integrating PdV. You know, you have to get the pressure expressed as a function of volume to integrate it. And now we're we're going to get something that has the same information in it. It just represents it in terms of some different variables. So we're going to start with this star equation. So from star, we're going to use the fact that the enthalpy is equal to U plus PV. Well, we have everything expressed as differentials, so we're going to write this as H is equal to U plus differential of PV. Now this should be, no, DH is equal to DU plus D of PV. And if we wanted to expand that differential of PV, how would you do that? It works just like the product rule. So yeah, so I'll write it as V dP plus P dV. And so now take this and combine them. And you get TdS is equal to, so now the du and the pdv are here, and so you can rewrite this as dh minus v dp. So I'll call this double star. And this one is a way to calculate entropy in terms of temperature, enthalpy, and volume as a function of pressure. A lot of the times that this is going to be useful are when you have, like, if you do problems where the pressure is constant, then equation star is going to be, the opposite. If you're doing one where the volume is constant, then there's not going to be any change in volume, and that term just drops out. If the pressure is going to be constant, then this term drops out. A lot of these, we're not going to end up using this full equation. We'll have simplifications that make it useful. And I'm going to do a couple of, before I do that, these, you can rewrite these in specific forms. So you have TdS is equal to du plus pdv, and TdS is equal to dH minus v dP. And you can also write it in the molar form. Okay, let me do a really quick example and then we'll move on. Yeah. You have that top one there? Are you okay here? Okay, so Yeah, so the specific ones are per kilogram, and the other ones are extensive. Yes, that's right. That always means per kilogram. Yes, it is. Yep. Dang it. Okay, so remember that entropy is a property. And so you can, if you're dealing with a substance that you have a table for, you can look up the entropy at a given temperature and pressure. And so, but, people have to calculate the values in those tables. So they're using stuff like this to calculate the values in the tables. And, a lot of times you won't have access for the material that you're dealing with, maybe a mixture that, a specific mixture of materials or something. So, okay, let's, yes.
Like specific heats or specific entropy is defined as partial derivatives of pressure, volume, things like that.
Or say it again.
Specific heat is
Yeah.
defined as the partial derivative
Yes.
with respect to volume or
Yes. Pressure.
right? Is the same true of entropy?
Of entropy?
Yeah. I'm sorry, specific
Specific entropy is just entropy divided by the mass. Yeah, so you don't have to think about it like that. Okay, so let's say we're going to calculate the change in specific entropy for water as it goes from saturated liquid to a saturated vapor at a constant pressure of 1 bar. Well, this is a simple example because when you're going from, if the pressure is constant, well, first of all, the pressure is constant. That's going to simplify these equations. And second, if the pressure stays constant, the temperature stays constant as this phase change happens. So P is also constant. Oh, cool. Yeah, right. So we can use this equation that says from state 1 to state 2 of ds, that's equal to 1 over, so I'm using the first of those two TDS equations. I divided the left side by t, so we have 1 over t here, times the integral from state 1 to state 2. No, I'm not using the second one. So, okay, look at what I'm doing. So, the pressure stays constant. So if you integrate this, it goes away. The temperature stays constant, so you don't have to integrate that. You can keep that outside of the integrals. And so we just have the integral of ds is equal to 1 over t times the integral of dh. So S at state 2 minus S at state 1 is equal to 1 over the temperature times H at state 2 minus H at state 1. And now you can look up all these values in the table. And you get that the change in specific entropy is equal to 1 over 372.78 degrees Kelvin. So at 1 bar, which is a little bit lower than atmospheric pressure, the temperature is just under 100 degrees Celsius at saturation. And then times the enthalpy at instant 2 is 2675.5. The enthalpy at instant 1 is 417.46. And so you get a value of 6.057 kilojoules per kilogram. And that is exactly the value that you'd get from just reading the change in entropy out of the table. And this should also have kilojoules per kilogram Kelvin. Okay, sorry, what?
Oh, I just said then temperature was constant.
Yeah, because if you don't change pressure, while you're changing phase, you're not changing the temperature. Any other questions?
Why did you drop the VDP?
Because P is constant. So if you integrate, that little increment that you're integrating over, if that thing doesn't vary, then the integral goes away.